And we are on. What? Okay, it said recording in progress. I've never actually heard it say. It usually doesn't say that. Okay, so maybe they've. I noticed people keep adding new features to their apps. And okay, so I'm going to turn off the participants view, and I'm going to turn on the little camera, with which you can actually see what I'm writing. And I hope the battery doesn't die. And okay, okay. So, oh rats! The reflection for the little camera, the reflection is right where these numbers are, and it's sort of where those numbers are. I just have to add these up. So this is 78, 108, 113. Still too big. Okay, I'm just trying to come up with an example. So this is 37, 21, 15, and then let's say 14. What's this? 58, 68, 73, 83, 87. Okay. 87, 90, 100. And then let's say P6 is 10. Is that just 100? Yeah, that's 128. P7 is also 10 out of 128. And P8 is 8 out of 128. If somebody wants, can you just quickly add those up? Okay, wait, there are messages in the chat. What am I doing? I'm just writing some numbers. So these should add up to 128. If somebody wants to check that and let me know, that would be great. Today, Huffman coding, 118, really trapped. In that case, I'm just going to add. This is 9. So okay, P9 equals. So I dropped it from 8 to 9, so it was 119, and then I'm going to have another 9 over 128. Okay, so that should be better. Is the first one? The first one is 37. Okay, so that's, I'm going to change this back to an 8. Okay, P8 equals 8 out of 128. Okay, so today we're going to talk about Huffman's algorithm. Now, I stayed up writing an extra proof, adding an extra proof to the chapter, so I didn't get enough sleep. So I'm a little bit out of it, which is normal for me. Okay, so before we get into Huffman coding, I have to tell you a little bit about information theory. So when we started the course, I was saying, I'm just going to check that this is recorded. And I asked for things, what has computer science accomplished that's comparable with everything is made of atoms, or the Earth goes around the sun, species rise, blah, blah, blah. And somebody suggested information theory, which is pretty deep. I don't really consider it computer science. I consider it electrical engineering. I think Shannon considered it electrical engineering. It's a little bit fuzzy because, for example, my first PhD supervisor he got his degree from MIT, where Shannon was and where all this stuff was happening. And officially, he was an electrical engineer, but he was a cryptographer, and he couldn't do anything like electrical engineering. But that was what it was called. What is information? Okay. So before Shannon, this paper, Shannon published this paper, a mathematical theory of communication, which is now generally referred to as the mathematical theory of communication, in 1948, and I think the Bell Systems Technical Journal or something like that, which was top notch. And so before that, there wasn't really a way for people to talk about information scientifically. I mean, you couldn't really measure it. I mean, how do you measure information in such a way that you can talk about it as scientists, like seriously? And I think still, even now, people like to think about information as somehow having meaning, as being important stuff. If I tell you if I tell you what the weather's like, that's not so much information as if I tell you that there's going to be an asteroid strike tomorrow. Now, actually, okay, so if I tell you something surprising about the weather, like lightning struck the same place twice, you're like, yeah, who cares? But maybe that's as unlikely as an asteroid strike. So actually, even if the probability is the same, you'd be like, yeah, well, I care about this one thing and I don't care about this. I care about this and I don't care about this. So the thing I care about somehow has more information for me. Let's forget that, okay? So we forget the meaning. We forget all the semantics and the consequences and the importance and the societal impacts and stuff like that of what this information is. It's just we consider that there's going to be some message and we have to transmit it precisely faithfully. Our job as electrical engineers, as computer scientists, is to get the message across. It's not to worry about what the message is about or what it will be used for or anything like that. We're just, we're doing communications. Somebody gives us a message, we just send it or store it in such a way that we can recover it. Now, there is lossy, oh, I have to start the timer. There is lossy compression, like MP3s and stuff like that. Okay, so I'm going to pause. I'm going to change this, and I'm going to change this to 20 minutes because maybe I've been talking for 5 minutes. Okay, wait, here, I can look and see. So I've been talking for 18 minutes. Okay. Start. Okay, so for example, MP3s. You have data compression there. You get fantastic compression with MP3s, MP4s, but the problem is they're actually throwing away a lot of information. Right? So it's not actually data compression, it's data reduction. And they do this by, you have this psychoacoustic model of the ear, so they know that the human beings can't actually tell if two sounds are very close together, which one preceded which one. So they actually get rid of that. The problem is you have to have this, and you can't tell differences in volume when they're very, very small, and certain loud noises will mask soft noises. And so they get rid of a lot of information. The problem is you have to have this psychoacoustic model of the ear. And like, who wants to do that? We want to do computer science. We don't want to do like psychoacoustics. This is disgusting. I spent 3 years of my life in a psychology department, and I want those back. We're not going to worry about this noisy stuff, this lossy compression. where you have to worry about, what does stuff, what value, what do you want to lose, what tolerance do you have? Forget that. We're going to worry about noiseless. So, so this idea is just somebody says, I want to send this. This is the universe of possible messages, right? And we don't care what those messages are. We just want to assign a code to those so that when somebody comes and says, okay, well, it was actually that. So you have a random variable, right? So Shannon said, like, we forget what the messages are, what they mean, and we just consider that we're going to stand here and somebody's going to come and tell us how an event turned out. Right? So there's this random variable. It's going to take on values according to a certain probability distribution, which we know, which is p equals p1 through pn, say. So it's a discrete probability distribution. And we, with the person at the other end of the communication channel, we've worked out a code where somebody comes and tells us, what value the random variable took on. We're supposed to transmit that value according to the code. And we want to choose this code so as to minimize the expected number of bits we need to send. Now, the code is supposed to be something called self-delimiting. So that means that every code word, when the person at the other end gets to the end of the code word, they know they're at the end of the code word. So sometimes this is called prefix-free because it means that none of our code words can be a prefix of any of the other code words, because if they were, then the person at the other end, when they get to the end, when they get to the end of the code word, which is a prefix of another, they don't know if the code word is, if they've seen that, or if they've seen just the start of this longer code word. Okay, so for example, it would be bad if I had a code word that was 00110, and I had another code which was 0011011. Right? Because if I send this message to the person at the other end of the line and they say 00110, they don't know if now they can stop or if they have to wait and get 2 more bits. Okay, so this, we don't want to have this. So instead, we want to design this prefix-free code. And Shannon said, okay, we look at the probability, we forget what the messages are. We just look at this probability distribution and we try to figure out what is the minimum expected code word length. So if somebody gives us a probability distribution, say P1 through P8, so these are just positive. So let's ignore the things with probability 0. So these are positive numbers that sum to 1. Okay, and this is all we're going to worry. We're going to build the code according to this. We're going to build one of these prefix-free codes. Now, in the notes I go through, Shannon said, okay, so information is the opposite of uncertainty. So how do we measure information? Well, it's how do you measure uncertainty? And it's the unit you use for us is a bit, which stands for binary digit. It was actually suggested to him apparently by Tukey, who was either Cooley or Tukey. It was one of the guys who rediscovered the fast Fourier transform. And a bit is your uncertainty about the outcome of a fair coin flip. So if you have an event and it's 50% one outcome and 50% another, and before this happens, your uncertainty about that is 1 bit, right? So what is your uncertainty about the roll of a 6-sided die? It's actually, well, it's more than 2 bits, because you can express any of these outcomes with you can't express all of the 6 outcomes with 2 bits, but you can with 3. So it's something between 2 and 3. It's actually log base 26. Okay, so this is not an information theory course. I stuck into the notes Shannon's axioms of uncertainty. And then, so the main thing for us, 20 minutes have passed already, oh, 15. So for us, the important thing is this problem of building a code given a probability distribution. Okay. Shannon came up with, he came up with this thing called the noiseless coding theorem, which said you have a measure on any probability distribution. So if P equals P1 through Pn, then you have this measure called H of P, the entropy, which is, well, a lot of people put the electrical engineers tend to put the minus sign out in front. We just flip the fraction in the log. So this is pi log pi. So he showed that he gave these axioms of uncertainty, saying like, okay, if all the probabilities are uniform, then the uncertainty increases as the number of possibilities increase. And if you break the events up in a certain way, then you know the uncertainty has to be the uncertainty of the first part plus the uncertainty of the weighted uncertainty of the second part, blah, blah, blah. It's in the course notes. So he showed that entropy, this is the only function that fits in the ML. Oh yeah, but read the notes, see if I present it nicer. So I used to do this stuff way back when, like 20 years ago. I was into, actually, I'm still on the data compression program committee of the data compression conference. I do compress data structures. So I do data structures and data compression mixed. So these are sort of I couldn't decide which one I liked more. So my take on stuff is different from machine learning. Okay, so notice I haven't put a subscript on the log. That's because changing the base of the log changes the constant, right? And right, so if this is log 2 or log 10 or log base e, then it just changes everything by a constant, and that changes the units you're working in. So if it's log base 2, you're working in bits. If it's log base e, you're working in this weird unit that the electrical engineers like called nats, because it's the natural logarithm, right? Okay. So you have this, and Shannon said, okay, you can't beat this. So the first part of the noiseless coding theorem, the lower bound, says you can't design a prefix-free code which has expected code word length less than this. Okay, so I'm going to put log because we're going to consider we're going to consider binary codes and we're going to consider bits. So he said you can't design a binary code where the expected code word length is less than this. What is the expected code word length? Well, it means that I design the code and then one of these events happens, chosen according to this probability distribution. Well, if my code words have length L1 to Ln, in this case 8, my expected code word length is sum over pi Li, right? So I send Li bits with probability pi. Okay. So he said you can't beat this. And actually, if we have time at the end, the proof of that, a rough proof of that, is in the lecture notes. That's what I stayed up and added last night. And if we have time at the end, I can sketch it. It's pretty easy, the lower bound, but it's not actually necessary for an algorithms course. And he showed that you can get to within 1 bit of this. You can get an expected, a code with expected code word length and most, well, actually strictly less than the entropy plus 1. So let's just quickly go through that. Watching to make sure this doesn't, 7 minutes, 12 seconds, okay. So what he did, he said, suppose, so I had to write these, I couldn't just come up with arbitrary number because I wanted them to be in order. Because Shannon said, okay, without loss of generality, suppose you sort the probabilities. Suppose the probabilities are sorted, okay. So what he did, he said, let SI equals sum j equals 1 to I minus 1. Can you read this at all? No. Okay, I'll write it a bit bigger. So we have these PIs. You could read those because you were working out what the numbers were. So we have SI equals sum j equals 1 to I minus 1 of pj. Is this better? Yes, okay. So the key property here is, and we view this as a number, right? It is a number. It's the sum of a bunch of probabilities. So it's a number between 0 and 1. So actually S1 is exactly 0. Okay? Because it's the sum from j equals 1 to 1 minus 1, which is 0, of pj, so it's an empty sum. Okay? So what so here we have S1 equals 0. S2 equals 37 over 128. S3 equals 58 over 128. That should be familiar because people just worked this out for me. Equals 73 over 128. S5 equals plus 1487 over 128. S6 equals 100 over 128. S7 equals 110. Wait. Right. Oh, I have two 10s. Good. S7 is plus the first 10 over 128. And S8 equals 128 over 128. So the last thing, if we added the 8, we would get 1. Okay? Now, the trick Shannon used was he viewed these as binary numbers. Okay? So binary fractions. So before I write these out, to give you this example, so notice that if you take two binary fractions, these are just like decimal fractions like 0.37125. Okay, before we get into the binary stuff, imagine that two numbers, 37125, something, something, something. So this is X, and this is Y. Okay, I tell you that these two numbers agree on their first 1, 2, 3, 4, 5, their first 5 digits after the decimal point, to the right of the decimal point. Okay, then what can you tell me? So I tell you that X and Y agree on their first 5. I tell you that X is less than or equal to Y. What can you tell me about Y minus X? You can say it's less than what? I'm waiting, watching the chat. Actually, while you're thinking, I could restart the little camera because it's been 25 minutes. Why? Yes, but specifically related to the number, the fact that these are five digits. I mean, is it possible that these two differ by like a tenth? So, okay, I'll restart this in just a second. But notice that the most y can be, so the smallest amount x can be is if this is followed by a whole string of zeros, right? If the part I didn't tell you, it's all zeros. And here you say, okay, well, how big can that be? Well, maybe it's followed by a whole string of nines, but no, it's not. Because if you have 5, 9, 9, 9, 9, 9, 9 for infinity, then you don't write 5, 9, 9, 9, 9, 9, 9. You write 6, 0, 0, 0, 0, 0, 0, 0, right? So y is actually less than this 5, 9, 9. So the difference is at most is actually the difference y minus x is less than 0.1, which is equal to 0.0000001111111999999 minus 0.00000. So it's less than this minus this, because this is bigger than y can be. This is as small as x can be, and that is exactly 1, 2, 3, 4, 5, 10 to the minus 5. Okay, reset. And I'm going to change this to 25. And restart this. Okay. And get that going. Do you believe me? 10 to the minus 10. No, so if no, I think if two numbers agree on, if I tell you that they don't agree on any of the numbers, wait, is it 10 to the, it differs by most. No. If I tell you that they're both 0 point, if they both start 0 point something, then they differ by less than 1. If they both start 0.3, then they differ by less than a tenth. If they both start 0.37, then they differ by less than 100th. Right? Because if they start at 0.37, what's the smallest? One can be 0.37000, and one can be 0.3799999, but that's still less than 100. If they differ on 3, they differ on less than 1,000. If they differ on 4, less than a 10,000th. If they differ on 5, they differ on less than 100,000, which is 10 to the minus 5, I think. Okay, so we've got quite a lot to get through. So it's not that, I mean, I wish I could spend more time on this because it's not that hard, but think about it, it's in the notes. Okay, so Shannon noted that, okay, so this works also in binary. If I tell you that two binary numbers, if x is 10110 and y is 10110 and x is smaller than y, then how much can these differ by? Well, now instead of being 10 to the 1, 2, 3, 4, 5, 10 to the minus 5, they can't differ by more than 2 to the minus 5, right? So if I tell you that two binary numbers are both start 0 point something, they differ by less than 1. If they both start 0.1 and 0.1, then they differ by less than a half. If they both start 0.10, they differ by less than a quarter, right? So if they agree on B bits, they differ if two binary fractions agree on their first B bits after the binary point, then they differ by less than 1/2 to the b, which is 2 to the minus b, okay? I know it's going a bit fast. I mean, packing information theory, packing noise with coding theory, and I still want to cover Huffman coding. Ha. So this is a bit of a dense class, but so this isn't too bad. It shouldn't be too bad if you think about it in terms of decimal numbers, and then I'll take that as a compliment. I'm on track to not having anyone say that my course is easier than Norbert's. Okay, so if you take this and then you flip it around, you say, okay, if two numbers differ by a lot, then they can't agree. If two numbers between 0 and 1 differ by quite a lot, then they can't agree on very many on very many of the bits to the right of the decimal point. Right? So actually, if they differ by d, then I think they can, if you flip this around, I get the floors and ceilings mixed up, but they can only agree, if they differ by an amount d, they can only agree on their like log d first, I think it's floor log d, floor log d. I'll have to think of it, okay. We'll see this. It's right in the course notes, I hope. So you can see that if it says they agree on if they agree on b bits, then the difference is less than 1/2 to the b. So if the difference is bigger than 1/2 to the b, then they have to differ on one of their first b bits. Okay. So if the difference is bigger than this, then they have to disagree on one of their first b bits. Okay, it's just the converse. So, and I think that is so if you differ by d, you have to differ on one of your first floor log d, floor log d bits. Okay. So why is that useful for building a code? Well, look, these are numbers between 0 and 1. Okay, so how much does S2, because the PIs were sorted, S2 differs from S1. So S2 minus, I'll make this bigger. S2 minus S1 is P1 by the definition of the S's, which is greater than or equal to P2. Okay, and what's the difference here? S3 minus S2 equals P2. So S2 differs from both its neighbors by at least P2 because the probabilities were sorted. So therefore, if we get rid of this, and we just check that this is recording? Yes. We work this out. So we say, okay, so we view this as a binary number. So S1 is 0.0000, so because it's 0. So S2 equals 0. And this is why I chose the denominator 128. So 37 is what? It's 32 plus 5, which it's not 64, it is 32, it's not 16, it's not 8, it is 4, it's not 2, it is 1. Is that right? Is that 30? If somebody has one of these cute little calculator things that converts between binary and decimal, this should be 37 out of 128. I think it's not. This is about a quarter. So this is a quarter plus 8 to the 16th, 32nd, whatever. Okay, we don't have time. Like, we hope it's true. So S3 is equal to 58 over 128, which is not 64, it is 32. 58, 32 plus, it is 16. 32 plus 16 is 48. It is 8. It isn't 4, it is 2. Okay, so I'm not going to do this for all of them. S4 is equal to 73, which it's 64, not 32. 73 is not 16. 60, it is 8. It's not 4, it's not 2, it is 1. Okay. So are people following this at all? These are just the binary fraction. These are just these sums as binary fractions. Now, by what we just wrote and erased here, because I don't have 3 boards, these numbers, so what S2 differs from S1 and from S3 by at least P2. That means that that it can't agree on too many of its first bits. Oh, I think it has, yeah, it has to be a ceiling. Yeah, it has to be a ceiling. So it has to agree, so S2 has to disagree. Sorry, I said floor and ceiling. With S1 and S3 on one of its first ceiling log 1 over P2 bits. Okay, because these numbers differ by at least P2, it has to disagree on one of its first ceiling log 1 over P2 bits. Okay. I know that's a bit fast, but I want you to sort of understand a little bit of information for you. Okay, so you get it in machine learning. Fantastic. Okay, so that means that, well, if we look here, that means that it differs from S1 on its second bit, and it agrees with S3 on its second bit, but that means that if we take this prefix, these 3 bits, 0, 1, 0, S2 is the only one of these that's going to start 0, 1, 0. So we can use 0, 1, 0 as the code word, as the second code word. And notice that 0, 1, 0, it has length 3, and indeed 1 over P2, so 128. So ceiling of log 128 over 37. This should be at most 3. Okay, so this is saying that So what is, this is 3. So this should be between 2 and 3. Okay, so you get this guarantee. So if you take, this has to be, right. So if we look at these code words, this is the code word. If we look at these fractions, we can pull out the code words for these numbers. So the first code word is 0, 0. The second code word is 0, 1, 0. The third code word is 0, 1, 1. The fourth code word, I can't see what, so it's S5 would be 87, so this would be 0.64, 70, 80. Yes, there's a, it's not a 32, it is a 16, and then it's not an 8, it's like this. So now we would say this one, it has to be 1, 0, 0, and this one has to be something else, okay? Oh, thank you. Why just the first 3 digits? Because if we figure, because it has to differ by, at least because it differs by P2 from the preceding sum and the succeeding sum, then we know that its binary representation has to differ by ceiling of log 1 over P2, and that's log 120, a ceiling of log 127 over 37, 128 over 37. And so that's going to tell us that it can't agree with these on too many of its bits. And in particular, it has to disagree on one of the first this many bits. And we look and we say, okay, it disagrees with S1 on its second bit, and it disagrees with S3 on its third bit. So if I tell you what I'm thinking of one of these numbers, and it starts with 0.010, you know which of these numbers I'm thinking about. 010 uniquely defines this. So if you take that prefix, that is not a prefix of any of these other binary fractions. So you can take it you can take the prefixes of these binary fractions as a prefix-free code. Great. Okay. We don't actually need to know that. That's just how Shannon did it. Okay. It's not that hard. It's described in the notes. I mean, when I say it's not that hard, Shannon was a genius. Nobody else had seen this. Like I said in the notes, Shannon's master's thesis was actually, he proposed using Boolean logic to model circuits. So like I said, if you thought assignment 2, that question about building adders was hard now, think about doing it when you couldn't actually talk about logic gates. You couldn't say that you're doing ands, ors, nots, XORs, whatever. You had to be, yeah, it does. Like, who could do circuit design without Boolean logic? That was Shannon's master's thesis when he was 21. Boolean logic did exist. I mean, Boole introduced Boolean logic and sort of laws of thought. Actually, this is cool. When you're doing machine learning, you've probably heard of Jeff Hinton, who was he was actually a prof at University of Toronto. Now he's at Google, but he's the guy who did backprop and he got the Turing Award. Hinton, I think, is the grandson or great grandson of George Boole. So anyway, which is weird because he's now proposing that. So he sort of opposes the idea that thought is logic, and so he's a family rebel. But anyway, yes, Boolean logic was around, but nobody thought that circuits were modeled by Boolean logic, or at least Shannon proposed, like, oh look, I can model circuit design using and, or, not, XOR, Boolean logic, which did exist. And he proposed this, and so it's been called the most important master's thesis of the century. That was his master's. That's not even what he's famous for. He's famous for information theory. But before he did information theory, he did a master's thesis, which was revolutionary. Okay, so Shannon was really good. So relatively speaking, this is not that hard. Okay, but what I want to, so I'm setting this up. I'm using like most of the class to set this up. You might not be 21 yet. You still have some time. Okay, so now we're going to talk about. Okay, I'm more. Okay, I'm not a Shannon either. So I wish I were 30. Yeah, wish I were under 40. Yeah, it's not bad. Okay, the alternative is worse. Okay, so getting back to, so Shannon came up with this construction of prefix-free codes, which I'm not going to follow through with the example. But, so Shannon was a genius, but this is not an optimal construction. It shows that, yes, if you take these things and you say the sum of these some people in the class are probably under 21. They could turn out to be Shannons, maybe. Okay, so if you take some, and you assume that you're going to use this many bits for the ith code word, a ceiling, you use that many bits for the ith code word, you're going to get pi ceiling log 1 over pi. This is strictly less than sum over the i's of pi log 1 over pi plus 1. This is equal to, since these pi's times plus 1, this is plus pi, and then sum over the i's, the pi's add up to 1, so this is just sum of I pi log 1 over pi plus 1, and this is h of p plus 1. So this is a strictly less, so Shannon code uses less than the entropy plus 1. We are not going to get to the proof of the lower bound, but it is in the lecture notes. Okay, so Shannon's construction, Shannon codes are good enough to prove that you're within 1 bit of optimality, within 1 bit of the entropy, and the entropy is a lower bound. But it's open, like, okay, but what if we actually want the best possible code? And is that 4 minutes remaining? Okay. So this was sort of an open. Shannon didn't see how to do that, and there's another construction which is similar to Shannon's, except instead of doing these fractions, you sort of split. Called it was by Robert Fano at MIT. And so that was about the same time. So this was in the late 40s. And then within 2 years, everyone realized that Shannon's information theory was fantastic. And so within 2 years, it was being taught at MIT as a graduate course. Sort of like, here's this new field. What can we do with it? And it was being taught by Fano. And one of the people in it was David Huffman. And so Shannon said, I would normally make a joke about like, I should do this, but I don't have time in this class. So Fano said, like, you can either write the exam or you can do a project. And for example, you can figure out an efficient algorithm for finding the best code. Because in the course notes, there's an example of a Shannon code, which is not as good as it could be. Where it's good enough, it's within 1 of entropy, but there exists a prefix-free code which is better. So so Huffman decided, okay, I'm gonna solve this. I'm gonna find the optimal code. And so he did. So the story goes that he couldn't figure it out, and he couldn't figure it out, and he was about to give up and start studying for the exam, and he finally figured it out. and it got published. It's Huffman's algorithm. He's famous for it. So we're going to cover that algorithm, but really quickly. So that's a greedy algorithm. So this is our introduction to greedy algorithms, allowing me to stuff a little bit of information theory into the course. Please read the lecture notes because it has lots of cool stuff in this chapter, and it took me ages to write that. But first, because we have this problem that Shannon didn't solve and Huffman only barely solved in time to avoid the exam, we're going to do a little bit of a warm-up, okay, just in the time remaining. And the warm-up is going to be, suppose, now in the last class we were talking about merge sort, okay? And imagine that I want to do an illustration of merge sort. So we're going to design a greedy algorithm for dealing with a problem related to merge sort, just as a warm-up. Okay, imagine that I take an array, and I want to illustrate how merge sort works. So I split it, it's unsorted. I split it into 2 unsorted subarrays, and I choose 2 people. I actually did this last year. I choose 2 people in the participants list, and I send them these 2 subarrays, and I tell them, okay, now recursively you split them up and send them to other people, and okay. But something goes wrong because it's online teaching, and it's just not reliable, and it's like people didn't hear, or people couldn't read the board or something. So what actually ends up happening is people recursively sort their subarrays, but then some people send them back to me directly instead of sending them to the people they got them from. So I get a bunch of sorted subarrays which all together form the whole array, but they're not merged together. Right? So do people understand the problem? So I have a bunch of sorted arrays, and I want, and now I think, okay, my demonstration didn't work. I'm going to sort them. I'm going to merge them myself. Okay, so I have a bunch of little sorted subarrays, and I want to merge them into one array myself. But I want to do this as quickly as possible. Okay, so let's suppose just to reuse these numbers, let's suppose that I get back an array of size 37 and an array of size, okay, so this is not to scale. Okay, maybe let's make this a bit bigger. And an array of size 15, and an array of size 14, an array of size 13, subarray of size 13, and 2 arrays of size 10, and 10, and 8. Okay, so these are the sorted subarrays I get back. And I want to merge them. Now remember, in the last class, I gave you this merging code, which would take 2 subarrays and merge them, and the time it took was proportional to their combined length. Remember? Okay. So now this is where I want to use that code, and I want to merge these into one array, and I want to do it as quickly as possible. So I'm going to do pairwise merges. I have to start this. I'm going to do pairwise merges, and I want to use the least time possible. So each pairwise merge takes, if I merge this one and this one, it's going to take time 25. If I merge this one and this one, it's going to take time 45. Do you understand? Is anybody there? Okay. So what are we going to do first? Now, I want to use the least time possible. What are we going to do? What would you suggest I do first to minimize the time I'm going to spend in total merging stuff? But I don't have a subarray of size 1 and 1. I'm going to choose 2 of these and put them together. Merge largest with smallest, and okay, so that's going to, well, but let's think, is that going, suppose that I had one that was of length 10 and one that was of length 1 and one that was of length 1, okay? If I merge, so I can do 1 and 1. Well, okay, let's do 1 plus 1 equals 2. Okay, so I do 1 plus 1 equals 2, and then I do 2 plus 10 equals 12. That's one strategy. But if I do 10 plus 1 equals 11, and then I do 11 plus 1 equals 12. So here I end up spending total time 14, and here I end up spending total time 23. So merge bottom to top. Well, okay, but I'm only worried about the first step. Now in the notes, I wrote that I have this friend, Jeremy, who is an expert on sorting stuff. And suppose that he's on his way over to help us merge these optimally. But he's a little bit late and we're a little bit impatient and we just want to worry about the first step. And then he's going to show up and he's going to take over. Okay, so what would the first step? So bottom to top would be, I would merge these 2. Merge the smallest 2. Okay, yes, so yes, let's suppose we merge the smallest 2. Note that somebody said this spontaneously. And actually last year, somebody said this spontaneously as well. And then it turned out I was so happy. I thought, oh, I've made this so easy. And then it turned out that that person was one of the best students and is now Norbert's grad student. But okay, so merge the 2 smallest. Okay, so let's suppose we merge the 2 smallest. So that's going to take these 2, and it's going to produce an array of size, a subarray of size 18. And then, oh, this is going to get tight. Okay, then if we were to, oh, that's cheating. Oh, okay, probably you may have actually seen Huffman codes before, but you may not have seen the proof of correctness. Oh, drat. Okay, so then what are the 2 smallest now? It's these, 23. And then what are the 2 smallest? These, oh, maybe this isn't a great example. It's 19, and then it's 21, no, it's 19 and 18, right? So 19 and 18, it's 29, 37. And then it's going to be, so which one? So it has to be, it's 37 and 21, which we can do here. And that's going to be 58. And then it's going to be 37 and 58. And this is, wait, that doesn't add up to, I made a mistake here. 18 and 23. Oh, crap, I had a 23 that I didn't see. Okay. So it was 19 and 18, yes, was 37. And then it would have been 21 and 23. And 23, which is 44. And then let's say it's 37 and 37, which is 74. And then it's 74 and 44, which is 128. Okay. Is it? No, it's 118. I missed something somewhere. But you can see what this process is. 15 plus 14 is 29. Yeah, okay. So, but you can see how this works. Okay, you do this offline at home because we have like 18 minutes left. Okay, so the question is, why does that work? Well, it works. Suppose that why, after we do this one step, so if we did the whole thing, that would be what it looks like. But let's suppose we just want to say that if we do this first step, we merge the two smallest, then we haven't messed up. Jeremy can show up and say, oh, it's not what I would have done, but I can work with it anyway. Okay, he can fix it. He can still reach an optimal solution. So we just want to prove that the first thing we do is not a mistake, that it can be extended to an optimal solution. So this is going to be tight, 18 minutes. Okay, so the idea is you can view a merging strategy. Like if you look at this, it has a bug in it, fine, but it looks like a tree, right? It looks like, in particular, a binary tree because we're doing pairwise merges. In fact, any merging strategy is a binary tree where the leaves have weights corresponding to the sizes of the initial subarrays. And when you merge, the internal load has the size of the resulting subarray, which is the sum of the two weights. Right? So you can view this as a binary tree where this would be like 10 and 8 and 18, and this would be 10 and 23 and 13, and this is a 23, and then you have and so it's you view it as a tree. Okay, now consider an optimal a solution where the so something else about this tree. What is the total time you use for a merging strategy? Well, notice that if you have this tree, and down here you have some leaf, so here is this leaf labeled 10. Well, so here is this leaf labeled 8. Okay, on all of the steps up to the root, all of these 10 elements, all of these 10 numbers are involved in those merges. So this 10, each element here costs you constant time in each of these merges, right? So this takes time 18. This takes time. So each node takes time for the merge proportional to the sum of the leaves in its subtree. Okay. Yes, this is supposed to be like the Socratic method where yes, actually, okay. But I don't know if you know that from data structures or if you're figuring it out. So, so you think, okay, the total cost of the strategy is the sum of these 10. How much time do they contribute? They contribute, each element here contributes time proportional to the number of merges, which is the depth of this node. So the total cost of the strategy is the sum over the leaves of V is a leaf of depth times size, well, times weight. So we can view this as the problem of, given a set of weights, n weights, we want to find a tree where the leaves are assigned those weights such that it minimizes the sum of the products of the depth and the weight. So depth V, weight V. Times weight V. Okay? So far we have this idea. We want to merge the two smallest first, and any strategy can be viewed as a tree like this. Now, I think the blue is getting faded. This is a red letter day. We're actually going to crack open the new markers. And we want the black. Okay, I hope this works. So imagine that somebody gave us an optimal tree. Okay? So somebody gives us, oh, isn't that nice? Somebody gives us this tree, this optimal tree, T-opt. Okay? And we're just arguing that our first step is not a mistake. So merging the first two is not a mistake. So suppose that the first two, okay, in our case, the first two are 10 and 8. So I'm going to use 10 and 8. Suppose that here is this 10, and over here is this 8. So these are these two leaves with weights 10 and 8. Now notice that if you swap two leaves where the higher leaf has a smaller weight than a lower leaf, and you swap them, it's still a valid tree. Like, it's still a merging strategy. And because we said the contribution of a leaf is its weight times its depth, if I swap something light that's higher up with something heavy that's lower down, then my cost gets smaller, right? Because I'm only changing two terms in this sum. So if I take U and V and I swap U and V, then U's term, the depth of what used to be the depth of U becomes the depth of V, and what used to be the depth of V becomes the depth of U. And so if I swap something heavy for something, if something light gets swapped with something heavy and goes that was further down, then the cost goes down, right? Maybe. I put that on airplane mode. Okay, suppose that here I have a 21. And here I have a 10. Okay, so this 21, these 21 numbers in this subarray, they're involved in every merge up to the root. So that means they're costing me, processing each of those numbers takes constant time in each of these merges. So that means it takes 21 here, 21 here, 21 here, 21 here, and 21 here in each of those merges. So that's taking me time, the weight, the size of the subarray times its depth. And here, maybe these 10 are only involved in 2 merges. So what would happen if I took this? So the 21 is contributing 1, 2, 3, 4, 5 times 21. So if I'm working out this sum, it's equal to something, something, something plus 5 times 21 plus something, something, something. And then over here, I've got this plus 2 times 10 plus, and then whatever the rest of it is. If I take this and I move this subarray and I swap these, so this is 21 and this is 10, then the whole cost of the tree is now going to be the same, except this is going to be 2 times 21 plus, this stays the same, plus 5 times 10. So I've just swapped these two and the cost gets smaller. Okay. So what I can do is I can assume that, now notice that this has to be a binary tree. So I've got 2 leaves. There have to be a pair of siblings on the lowest level. I can swap these with, let's suppose that this is 21, 21, and 14. I can swap these so that these two, the 2 smallest, are on the lowest level, and the cost doesn't go up. Okay, so if this tree was optimal before, when I swap them to make them at the lowest level, it doesn't go up. Now, actually, I could swap them to be at the lowest level, but maybe they're not siblings, but then I can, swapping weights at the same level doesn't change the cost of the tree. So when I do all this swapping, I get these 2 to be siblings. This is T opt prime is still optimal. So if T opt was optimal, T opt prime is still optimal because it doesn't cost more than T opt. So that means that there exists an optimal tree in which we merge those 2 smallest things first. So our first step is not a mistake. Jeremy can still show up and look at what we've done and say, oh, that's not what I would have done, but there still exists an optimal strategy. There is still a way to get to an optimal an optimal merging strategy from what you just did. So if we do the first step, merging the 2 smallest things, it's not a mistake. And then you think, yeah, but then the same argument is going to work on the second step. If we take the 2 smallest remaining things and merge them, then by the same argument, it's still going to work because it's a smaller subproblem. Once we've merged the two smallest subarrays, instead of working with n subarrays, now we have n-1 subarrays. So you would think this is going to work, and actually by induction it does. right? Because you think assume that it works on n-1 subarrays. It clearly works on 0 subarrays. It clearly works on 1 subarray, because 1 subarray is just the whole array. That's when my merge sort demonstration actually worked. It works on 2 because you don't have any choice. And then if it works on I, then it works on I+1 by this argument. So by induction, it works for all numbers of subarrays. I actually did the induction slightly differently in the lecture notes. Okay, so just getting to the punchline. So it's easy, you can see why this algorithm is correct, right? That repeatedly merging the 2 smallest subarrays is the right strategy. Okay, and it solves this. So more generally, given a set of n weights, we can build. Oh, I'm definitely not going to get to Van Leuven's algorithm today. I'm gonna do that as like an extra 10-minute segment. Everybody can leave, and I'm going to record something. Okay, so we can, given a set of n weights, we can build a binary tree whose leaves are labeled with those n weights, such that it minimizes the sum of the depth and the weight. Okay, so we're done the warm up, and we have 4 minutes left in the class for me to teach you Huffman coding. Now, unfortunately, it looks like a bunch of people already know Huffman coding, but now, so Huffman coding, the trick is you can view a prefix-free code. Oh, I erased that. I erased the code. But if, for example, you have a prefix-free code, remember that one was 0, 0, and 0, 1, 0, and 0, 1, 0, 0, 1, 1, 0, and something like that. You can view this as a binary tree. 0, 1. Okay, so 0, 1, 1, where each left branch, and then let's just say you have, okay, so then you have a 1, so 0, 1, 1, 1, and then 1, 1, 0, and 1, 1. 1, 0, and 1, 1. So this is a prefix-free code. You can view it as a binary tree. What is the code word length? It's the depth. So if you want to minimize the expected code word length, the weights, you assign the weights, the probabilities as weights to the leaves, and then it's the same problem. It's just build a tree that given a set of positive weights minimizes which are to be assigned to the leaves, minimizes the sum over the product of the leaves weights and depths. Okay. Why do I do it this way? It's because I've never had anyone who hasn't seen Huffman coding before ever suggest taking the 2 symbols assigned the smallest probabilities and making them the children in the code tree of a new node. Nobody has ever just spontaneously thought that up in one of my classes, and I've taught Huffman coding quite a bit. But if I teach it like this, ooh, here you have little subarrays and you want to merge the subarrays, then this is actually 2 classes where, okay, it's not entirely spontaneously because people did actually see Huffman coding before. But you can see, like, yeah, it's not that weird that if you had all those subarrays, and I say, okay, well, if it takes you time proportional to the length to merge 2 subarrays, what's the sort of obvious greedy first step? It's to merge the 2 smallest. That's not so weird. But yeah, like Shannon, if you're just talking about it in terms of prefix-free codes, Shannon didn't see it, and it took Huffman lots of tries before he saw it. So I like teaching it in terms of these merging subarrays. And I pretend it's a warm-up, but it's actually rediscovering Huffman's algorithm. And I am out of time. So we are not going to see van Leuven's algorithm, which is a shame, but it's in the course notes. And it's really cool. So everybody can go. Yeah, everybody can. I'm going to record it, but like this afternoon. I'm not going to do it now. So the nice thing about van Leuven's algorithm is Huffman's algorithm, you could implement this with a priority queue, right? Like you just take the two, you like extract the two smallest things, you merge them together, you take their sum and you put that back into the priority queue. So you know priority queues that do everything in logarithmic time. So you could implement Huffman's algorithm in, somebody actually said it a while ago, n log n time. So that's not bad, but then you think, okay, but what if, is that the fastest you can do? And it turns out that if somebody gives you all the probabilities in sorted order, then you can do it in linear time. And the reason I want to use van Leuven's algorithm is because I'm 1 minute over time. I know I'm going to end like right now, is because it shows you that you can use data structures to speed up your algorithms. Because van Leuven's algorithm uses two queues in a really sneaky way. Not really sneaky, it's not too bad. If you use two queues in this cute way, then you can do it in linear time if the probabilities are already sorted. So one of the things that I want you to get out of this course, which is actually, I believe, a learning objective, is that clever use of data structures makes algorithms faster. Okay, so we didn't see van Leuven's algorithm, we didn't see the proof of the lower bound, but they're in the lecture notes. So if you want to see them, you can read them. And I'll record something about van Leuven's either this afternoon or someday. Or it's actually, I can post the video from last year. You did van Leuven's? This was in 2110, but you didn't do AVL trees. Like, where are the priorities being set? You did AVL trees, but some people have posted, no, some. Okay, so assignment 4, I'm going to wait because assignment 4 is going to be, I was going to post it, it was just going to be Huffman coding van Leuven. But now I'm going to wait and it's going to be minimum spanning trees and some greedy vertex cover and some stuff like that. So, so it's going to be, oh, I think yeah, the little camera just stopped recording. So we're 3 minutes over time. Srini's class in 2020. You really did van Leuven's algorithm. Though the one that does the Huffman construct. Wow. Okay, in second year. Impressive. So anyways, if you want to review it, it's in the lecture notes. It's also, I can post the video from last year. But some people didn't see, okay, of the people who are still here, did anybody not see AVL trees? Because 2 people have posted on the Brightspace discussion board that they haven't. Yeah, so that happened to me a couple of years ago as well. Like 1/2 of the class had Edelson-Velsky-Landis. Okay. Yeah, it's dynamic balanced binary search trees. So I guess I'm gonna have to do it. Which, oh, this is a very full course. Okay. Okay, I'm gonna stop the recording. People can go because we're a few minutes over time. Oh, so we didn't see everything I wanted to in this class, but it's all in the course notes. Probably more or less right. Okay, so you sort of see how this proof of correctness goes. Don't worry, you'll see lots of more proofs of correctness of greedy algorithms. But this sort of, okay, yeah. Cheers, I'm gonna stop the recording now. And then I'm gonna go and have lunch. Yeah.